Today we're going to start this video talking about the answers in chapter 22 of your physics book. And the first thing that's very important to understand in chapter 22 is something called the right-hand rule. In order to do the first couple of problems in this chapter, you have to start out by understanding the right-hand rule. And I suggest very significant place in the book that you probably should go to. It starts in section 22.4, which is on page 782. If you look at figure 2217, this will help a great deal with understanding the right-hand rule. In order to do the right-hand rule, first of all, I know it's going to sound silly, but you have to use your right hand. And sometimes people don't do that, and they use their left hand and they get it backwards. The second thing you notice is that with the right-hand rule, you always point your fingers in the direction of the field. Your thumb goes in the direction of the velocity of the particle or whatever it is that's moving, and then your palm will always face in the direction of the force. Now this is true for positive particles that are moving. If you're dealing with a negative particle, it moves in the opposite direction. So positive particles, your palm will reflect the direction of the force, and you can see the formula right underneath it. It says, and the formula for calculating the force is F is equal to the charge of the particle times the velocity of the particle times the field. And then there's a sine theta, where theta is the angle if the angle is not 90 degrees. For example, if you have a field like this represents the field, and this is the velocity, then this angle right here is theta. In this case, I've drawn it as a right angle, and the sine of 90 degrees is equal to 1. And so if they're right angles to each other, then you don't have to take that into account. But any other angle other than a right angle is going to have some factor. And when you talk about the maximum is when these are at a right angle. And in the case that I've drawn here, the field is going to come out of the board into your face, not go into the board, but come out of the board. And so if you put your fingers facing up and your thumb facing to the right, then your palm will be facing up on your right hand. And so that's the direction that the field is coming out of the board into your face. Okay, so with that introduction, let's now move over to the problems that are related to this. And actually, the first couple of problems are a practice of the right-hand rule. So number one, it says, what is the direction of the magnetic force on a positive charge that moves as shown for each of the 6 cases? So the first one, A, you have the field coming out of the page, so your fingers should face out from the page. The velocity of particle is down, so your palm is facing to the left, and so the direction of the field on A is to the left. B, now you have the field is to the right and the velocity is up. Your palm is facing into the page. So the answer to number 2 is into the page. Number 3, or C, now you have the field going into the page. The velocity is moving to the right, and so your palm will be facing up. So up is the right answer. D, the angle here is 180 degrees between beta B and V, and sine of 180 is 0, so there's no field, or no force in this case. E, the field is into the page, the field is into the page, and the velocity, no, wait a minute, the field is up, the velocity is into the page, and so the field is to the right. And then the last one, the velocity is into the page, the field is to the right, and so the velocity is coming out of the page at U, the field is to the right, or to the left, and so the direction of the force is down. If you have any trouble with these, we can do these in class next week. B, or number 3, is the same exercise, but now we're talking about a negative, so it's going to be in the opposite direction of these. And so, for example, you have the field going into the page, the force is up, so your palm is facing to the left, but because it's a negative, the field, or the force, is going to be to the right. It's going to be to the right. B, the force is up, the field is to the right, the force is up, your palm goes, the force is up, the field is to the right, and so your palm is into the page, so that means it comes out of the page. Lastly, the field is going into the page, the force is to the left, the palm goes, no, wait a minute, I'm sorry. Yeah, I got it right. The palm goes down, so that's down, or up, excuse me. So there's those 3. Number 7. Now with number 7, we start doing some calculations. Number 7 states, what is the maximum, so it's telling you that the angle is 90 degrees, force on an aluminum rod that has a charge, so Q is 0.1 times 10 to the minus 6 coulombs. The magnet is 1.5 Tesla, Tesla being the international unit for magnetic field, and V is 5 meters per second. And so we use this formula up here, and the sine of 90 degrees is 1, so we don't have to worry about that. So the force is going to equal 0.1 times 10 to the minus 6 times 1.5 times 5. And so that multiplies out to an answer of 7.5 times 10 to the minus 7. And it's going to be perpendicular to the direction of the field and the velocity of the particle. It didn't give us the direction or velocity, so you can just say that it's perpendicular to both of those. Number 13. Number 13 states a proton, and we know that a proton has a mass of 1.67 times 10 to the minus 27, you'll need to know this, kilograms, and it has a charge of 1.6 times 10 to the minus 19 coulombs. It's moving at a velocity of 7.5 times 10 to the 7th meters per second, which is just a little short of the speed of light, perpendicular to the field, and a radius of 0.8 meters, okay? And this is one of the examples of when you have something moving in a circular path, which is what this says, what the formula for that, if you look it up, is that the radius is equal to mv over qb. Now what it's asking here is what is b, so if you solve this for b, you get mv over rq, and so you're going to get 1.67 times 10 to the minus 27 times v is 7.5 times 10 to the 7th divided by r, which is 0.8, times q, which is 1.6 times 10 to the minus 19. And if you do the math here, you get a field strength of 0.979 Tesla. Number 16 basically says to do the same problem, but this time we're talking about a electron instead of a proton. So the mass is going to be different. The mass of a electron is 9.11 times 10 to the minus 31. The charge is the same, 1.6 times 10 to the minus 19. The velocity is the same, 7.5 times 10 to the 7th, and we need to use the field strength from this previous problem, so 0.979 Tesla. So R is equal to mv over qb. So m was 9.11 times 10 to the minus 31 times 7.5 times 10 to the 7th divided by 1.6 times 10 to the minus 19 times 0.979. If you do the math here, the radius of this circular path is going to be 4.37 times 10 to the minus 4 meters. So that's the path that that electron would take if in the same setting. Number 24. Number 24, we're talking about something called the Hall effect. And the Hall effect is the generation of electrical potential when you have electricity traveling through a length of wire in a magnetic field. And the generation of the EMF that's generated is equal to the field strength times the length of the wire times the velocity of the particle or electrons that are traveling through it. So let's take a look at number 24. What is the speed of an supersonic aircraft that has a 17-meter wingspan if it experiences 1.6 volts of Hall effect between its wingtips when in level flight over the magnetic North Pole, which is the Earth's pole? Okay, so the length is going to be the wingtips, or 17 meters. E is 1.60 volts, and B is the Earth's gravitation or magnetic field, which is 1.8 times 10 to the minus 5 Tesla. Now, if we rearrange this equation for V, we get E over BL, and so that's going to equal 1.6 and then 8 times 10 to the minus 5 times 17. And if you do the math here, you get 1180 meters per second, which is cooking. I'm going to do the next problem because it also has to do with the Hall effect. And this one says a non-mechanical water meter can utilize the Hall effect by applying a magnetic field across a metal pipe and measuring the Hall voltage produced. What is the average fluid velocity in a 3 centimeter diameter pipe with a field of 0.5 Tesla and a voltage that's generated, which is 60 millivolts. Okay, if we say that this is E is going to equal BLV, so we want to know what that velocity is. So V is going to equal E over BL, which is equal to 600 times 10 to the minus 3 divided by 0.5 times 3 times 10 to the minus 2. And if you do the math on this one, you get 4 meters per second.